And now picking up, now we have with chapter 2, and we will be continuing on with functions. And for what we have in today's lessons, okay, we have something we have encountered time and again, and that has been with quadratic functions. And we've dealt with these in a sense through quadratic equations, like working with solving for second order equations, like using the zero product property, the square root property of equality, as well as the quadratic formula. And for what we have as a formal definition, and we have for quadratic functions, okay, and we have a quadratic function is a second order function whose standard form is going to be, okay, where we have y is equal to f of x, and f of x being one of the notations in the functional form that we have to represent y. And we have that set equal to ax squared plus bx plus c, okay, and we have whereupon, okay, a does not equal to 0, okay, and okay, so again, quadratic function, okay, this is going to be a second order function, and the second order is in reference to, okay, the highest degree of what we have in the independent variable which we happen to have at x, okay, and again, so we have one form of the quadratic function we had to be the standard form. And again, this is where we have the trinomial expression fully laid out as ax squared plus bx plus c. Now, there's another form we're going to be looking at. Now, personally, in terms of solving problems, I normally go with the standard form of a quadratic function. But there is another part, and the first section we have in chapter 2 is going to reference what is regarded as the vertex form. And in the case of the vertex form of a quadratic function, okay, you're still going to work with the letter A. All right, okay, so we have for the vertex form of a quadratic function. And this would be another way of saying the exact same thing. And for what is regarded as the vertex form, okay, so we have that y is equal to f of x, which is equal to a times the quantity of x minus h raised to the second power plus k. And like what we have in the standard form, okay, we still have that the leading coefficient a cannot be 0. Okay, and now for features of what we have in the case of the quadratic function, okay, so we have again, so you had the same letter a, and regarding a, if we have that a is a positive number, so we have that if a is positive, okay, then the graph of f of x is going to open up It's going to open up, okay, from what's going to be regarded as the vertex. And for what we have on the other hand, okay, if we have that the leading coefficient a is negative, then you're going to have the graph to open downward from the vertex. Okay, so the vertex, okay, again we have designated by the coordinate scale, which we have expressed as h and k. All right, and now some features regarding the quadratic function. Okay, so in terms of whether it opens up or opens down, that is contingent upon the sign value of the leading coefficient a. And now there's another item. It's not the graph itself, but it is used for proportional purposes. Okay, we have what's referred to as the axis of symmetry. And we have with the axis of symmetry case, you have x is equal to h. And by definition, okay, that is going to be a visual vertical line. Okay, it's going to divide the graph of the function into equal halves that will mirror each other. Okay, now regarding the vertex, the ordered pair again consists of the coordinates h and k. And this is going to be the location from which the graph of the quadratic function is going to open. So again, okay, this is your quadratic function. Again, it is a second order function. This is the standard form, and we'll be looking at translating between standard and vertex forms. So again, this is the vertex. So again, this is the general format. If A is positive, the graph opens. If A is negative, then the graph opens down. Okay, and again, we have the vertex. This is going to be the location from which the graph of the quadratic function is going to open. Now regarding quadratic functions, now the graph of a quadratic function is going to be a parabola. And say if it's opening upward, it's going to be looking like something between a U and a V. And just in the case of quadratic functions, okay, so just a couple of situations here. Again, just starting out with the x-axis and the y-axis. Okay, and so we'll have, in the case of a parabola, that is going to open upward. Again, we have the vertex HK. and splitting up the graph of the parabola. Okay, to have the axis of symmetry. Okay, so we have this case, right? So this point, HK, that is the vertex. And in the case of the quadratic function, okay, so again we have f of x, and we have is equal to, again with the standard form, so we have ax squared plus bx plus c. Again, the vertex form, we have a times the quantity of x minus h squared followed by the addition of k. And okay, so you have this graph is opening upward. So for what we have here, okay, so you have that a is positive. And again, since a is positive, okay, we do have that f of x opens upward. And it's going to open upward from the vertex. And I'll say something about the vertex itself. Now, the other week, we looked into items like relative minimum, relative maximum, and the relative maximum was where you had an increase followed by a decrease, whereas relative minimum was a location where decrease was immediately followed by an increase. And for what we have in the case of the vertex itself, because it's opening up from the vertex, so this vertex is going to be the minimum. Okay, because that is the bottommost point of what we have with the graph of this particular quadratic function. Okay, now let's say that in our other scenario. Okay, so we're still going to have HK, the axis of symmetry. And say if I just change the dynamic here, where instead of moving upward from the vertex, okay, we're going to have this be moving downward. Okay. Okay, so I had the function f of x. Now you still had the same general layout, okay, for the standard form as well as the vertex form. And this time, this is a situation where the leading coefficient a is going to be negative. Okay, so if a is negative, we have that a is less than 0. And this time we have f of x is going to open downward from the vertex. Okay, and if you notice, okay, we have a little change up. Okay, so we got that the vertex is going to be at the top point, and this time around the vertex is going to be the maximum. So again, in both situations, okay, so if A is positive, graph opens upward, vertex is at the bottom, and that is the minimum. Can you have the reverse situation? Okay, if A is negative, then the graph opens downward from the vertex. Vertex is the top point, so that will be regarded as the maximum of the function. All right, now just some early parts of the mechanics involved in what we have among the features of a quadratic function. And let's say that if you have a quadratic function, and let's say we have given f of x is equal to the square of x minus 2, followed by the addition of 5. Okay, and let's say if we were to determine, first of all, okay, the direction that the graph is going to open. Okay, in terms of where it opens, okay, that's just contingent upon the sign value, the leading coefficient in the vertex form. So again, we have for the general layout for the vertex form, so we have f of x is equal to a times the quantity of x minus h, quantity squared plus k. We have again f of x, then we have is equal to x minus 2, quantity squared, plus 5. Okay, so in terms of the direction, okay, so if A is positive, the graph opens. If A is negative, the graph opens downward. So if you notice, okay, we have k at 5, x minus h represented by x minus 2. Now we don't have anything explicitly in front of the parentheses, okay, but you'll read this as if it were 1. Okay, so we have that a is equal to 1. 1 is positive. So this means that the quadratic function is going to open upward from the vertex. Now, let's say just feature we have, again, among the traits we have regarding a quadratic function. Again, if you were to determine the axis of symmetry, okay, and this is where the h is going to come in. Okay, so we have in this particular case, right, so while we're not working with the zero product property, the h value is going to be the 0 of x minus h. Okay, so just from just kind of stepping to the side here, okay, so we have like x minus h is equal to 0, and you have the axis of symmetry is x is equal to h. Okay, now we have x minus h represented by x minus 2. So for this particular function, okay, setting it up, okay, so we have x minus 2 is equal to 0, and from which we have x is equal to 2. So for this function, and we have the axis of symmetry is going to be at x is equal to 2. Now, along with the direction that the graph opens, as well as the axis of symmetry, okay, we have looking for the vertex. So, for the items that we have here, okay, so we have x minus h represented by x minus 2. And again, okay, so we're going to have that, again, we had the axis of symmetry was at x equals 2. So you can say that, in this case, taken from the page, okay, we have that x is equal to h is equal to 2. Now for k, okay, we have plus k is represented by plus 5. So in this case, we'll have that k is equal to 5. So for the vertex, okay, we have hk, and for the coordinates specifically, okay, the location is going to be at 2, 5. Okay, so just for starters, okay, so the graph opens up from the vertex with the vertex at 2, 5, and again, you have the graph split up by the axis of symmetry, which we're going to have at x is equal to 2. Okay, if the binomial happened to be x plus 2, and I set it equal to 0, I would have that x is equal to negative 2. Yeah, so if you have your x minus h represented by a binomial of addition, your h value will be negative. But if you have, say, a binomial of subtraction, like in this case, your h value is going to become positive. Okay. All right. So just, in fact, I'm going to, I already think I have this visual available. See what I have in the, let's see. Oh, here we go. Yeah, I took this one, okay, this is out of Desmos. And anyway, so you have the quadratic function case. You have y or f of x is equal to the square of x minus 2 followed by the addition of 5. And just the for the other articles, okay, of information, okay, so you have the axis of symmetry. Okay, so this is what we have with x is equal to 2. Okay, so we have yeah, so this is your axis of symmetry. In other words, it divides up the graph of the function into 2 equal halves. Okay, so for what I have in green, say y is equal to f of x is equal to the square of x minus 2 followed by the addition of 5. And again, we have with the vertex okay, so that's going to be located at 2, 5. And notice, okay, the graph opens upward from the vertex. Okay, and so in this case, the vertex is going to be the location of the quadratic function's minimum. So the quadratic function has a minimum, and that is going to be the vertex. Okay, now situation where we can have another quadratic function, and just a little bit of a change up in terms of the dynamics as well as the sign values. And we have, and let's say that if we have, again, so we have just for the general layout of the vertex form. And we have the function to be whereupon we have -2 times the square of x plus 5 followed by the subtraction of 10. All right, so just looking at what we have in this layout. Okay, so for your a, h, and k values, okay, so you have a corresponds to -2. So a is negative. That is, a is less than 0. Okay, and so if a is negative, okay, this signals that the graph of f of x is going to open downward. And for what we have in correspondence, now we have x minus h represented by x plus 5. And if I set the binomial x plus 5 to 0, okay, so I have x is equal to -5. And so for that which will represent your h value, is going to be the result for x. So you have x is equal to h is equal to -5. And for what we have in the case of the k value, okay, because we have subtraction at the end, we have the k is equal to -10. Okay, so again, the leading coefficient a is -2. Okay, and because of the sign value, the graph opens downward. And we have for the axis of symmetry, okay, axis of symmetry, this is going to be x is equal to -5. And combined with k, okay, we're able to arrive at the vertex. And the location of the vertex, okay, it's going to be at -5, -10. And just looking at how all this is going to interact. Okay, so the graph opens down. Axis of symmetry, we have at x equal to -5. And again, the vertex we have at -5, -10. Okay. Okay, so what I have here, just for this section. Okay, so you had the axis of symmetry. I'm just going to sort of abbreviate AOS for axis of symmetry. So that is x is equal to -5. And notice, okay, now the axis of symmetry is going to pass through the parabola at the vertex point. So you have your vertex at -5, -10. And notice that this is a top point here. So the location of the vertex, because it is the top point of what we have for the parabola, okay, this one is going to be a maximum. And once again, okay, the a value is at -2, and so the direction to which the graph would be opening would be going down. Okay, so this graph here is for that of f of x equal to -2 times the square of x plus 5 followed by the subtraction of 10. Okay, and tell you what, just for the next few moments, let's say that if you have for given functions, so this given first, then we have second, we have f of x is equal to -2 times the square of x plus 6 plus 25 Let's see what we get for the following. Okay, so you have the direction f of x opens, and then the axis of symmetry, and then the vertex. Okay, so for both of these functions, let's see what we get for the direction that the function is going to open, the axis of symmetry, as well as the vertex. Okay, tell you what, if we look into the first function, okay, so we have f of x is equal to 3 times, okay, the square of the binomial x minus 7. Okay, and just looking at answering the 3 items, so we can go ahead and identify what will be a, h, and k. So again, we have a and 3 correspond together. Okay, so we have the a is equal to 3. Okay, and since a is positive, okay, this is going to mean that we have in consequence, okay, that f of x is going to open upward. Now for the h value, okay, so x minus h is represented by x minus 7. Okay, and so for the h value, this is going to be the 0, the x minus h expression, and the 0 is going to stem from, in this case, x minus 7, which is set equal to 0, and from this we have that x is equal to 7. And as for the k value, okay, notice we don't have anything added or subtracted, so right away it's going to follow this. Since we have a void, we're going to have that k is equal to 0. Okay, so we have with x equal to 7, okay, it's going to follow that we have that x is equal to h is equal to 7. And 2 key items of information we're going to have to follow. Okay, we're going to have the axis of symmetry. It's going to be at x is equal to 7. And for what we have in the case both h at 7 and k at 0, we're going to have for the location, the vertex, that is going to be on the x-axis at 7, 0. Okay. So you have just with the visual layout on this one. Okay, so if you notice in the graph case, you have y is equal to 3 times the square of x minus 7. And again, we have the axis of symmetry. Okay, so you have x is equal to 7. And again, we have the parabola opening upward. And again, the green parts. Okay, that is in reference to f of x is equal to 3 times, okay, the square of x minus 7. And once again, the graph is opening upward. And once again, we have with the vertex at 7, 0. Okay, this is the bottommost point. And for what we have here, that is going to be the function's minimum. So it's a bit binary. The vertex is either going to be a minimum or a maximum. And that is contingent upon how the graph is going to open. Right. Now, for what we have in the case of the other quadratic function, okay, so I had negative 2 times the square of x plus 6 followed by the addition of 25. Okay, so you have another vertex layout, and there is, we have all non-negligible values for all of A, H, and K. Okay. So we have at the front case, so we have representing A, have the A is equal to negative 2, and the sign value of A is negative. So this means that f of x is going to open downward. And x minus h, okay, now the general format has a binomial of subtraction. And we have here not a binomial of subtraction, but one of addition. So for what we're going to have here, the h value is going to stem from the 0 of setting x plus 6, the binomial. Okay, so if I set x plus 6 equal to 0, I have that x is equal to negative 6. Okay, so I have that x is equal to h is equal to negative 6. And we have with the 25 added at the end. Okay, so I have that k is equal to 25. And with both h and k identified, okay, especially with h, okay, again, I'm able to get both the axis of symmetry, whereupon we have x is equal to negative 6, and along with k at 25, okay, so for the vertex hk, we had the ordered pair at negative 6, 25. And again, the graph is going to open downward. So looking at what we have here, okay, so you have a downward opening parabola. And again, the vertex have negative 625. And again, just this line that we have in purple, the dividing line, again, that is the axis of symmetry. X is equal to negative 6. And again, we have for the graph itself, okay, we have representing negative 2 times the square of x plus 6 followed by the addition of 25. And again, we have with the peak point have negative 625. And since that is, again, it's binary, the vertex is either going to be a minimum or a maximum. And since the graph is opening downward, this has the vertex situated at the very top. So the vertex is a maximum. Right. So again, we have just in the laying the foundation. Okay, again, we have the direction the graph opens, as well as the axis of symmetry in terms of how the graph is going to be split up. And also we have the vertex from which the graph is going to open. And just sort of building upon those particular elements of foundation. Okay, if I were to add to the features, and let's say that just adding some building blocks, okay, to the graph to further define a quadratic function. Okay, and let's say that if you have a function f of x, and we have is equal to, and we have the square of x plus 4 minus 4 and we were to determine the following. Okay, so just once again, just in the somewhat familiar terrain, you have the direction that f of x is going to open. And once again, the axis of symmetry. Again, we have the vertex. And in terms of any additional stuff potentially, okay, we'll be looking for the intercepts. As well as the y-intercepts, or y-intercept rather, okay, if any, and also at least 5 points. Okay, so just once again, starting out, going ahead and identifying the A, H, and K values. So again, we have f of x is equal to the square root of x plus 4, followed by the subtraction of 4. And again, we have implicitly. Okay, so there's nothing in front of the parentheses, but you just read this as if it were 1. Okay, so again, we have that a is equal to 1. So a is positive. So this means that the graph of f of x is going to open upward. And in identifying the h value, okay, so x minus h is represented by x plus 4. So if x plus 4 is equal to 0, we have that x is equal to negative 4. And with x, in this case at negative 4, that's also going to be the h value. So x is equal to h is equal to negative 4. And guess what? For the k value, we have the subtraction of 4. So k is at negative 4. So the graph opens up, and we have the axis of symmetry. That's going to be x is equal to negative 4. And for the vertex, okay, both h and k are the same at negative 4. All right. Now, crossing over to the determination of the intercepts. Okay, now we briefly looked at those like the other week. And again, for determining x-intercepts, you're solving for x as y is set to 0. And so looking at where the graph is going to cross or touch the x-axis. So we're going to have here, okay, so again we have y is equal to f of x is equal to the square of x plus 4 minus 4. Okay. And again, so again, you're looking at setting y to 0 while solving for x. Okay, so we have in the build-up, we're going to have that 0 is equal to the square of x plus 4 minus 4. So you're setting y to 0 and solving for x, and looking at isolating the x expression. Okay, so isolating the x expression, which is right now the square of x plus 4. I'm going to add 4 to both sides. So we have that 4 is equal to the square of x plus 4. And what I'm going to do here is I'm just going to switch the sides here, going from the b is equal to a to the a is equal to b format. Okay. Now you could square out x plus 4 and set up a quadratic equation standard form, but what I'm going to do here instead is utilize the square root property of equality. Again, if you recall, if you have x squared is equal to p, x is equal to plus or minus the square root of p, and applying the same treatment, but where x is represented by x plus 4. So if we go from second to first order, we have x plus 4 first order is equal to plus or minus the square root of 4 and so I have x plus 4 is equal to plus or minus. Now the square root of 4 is going to be at 2. and looking at what we're going to have in x. So we have at the lower end, we have the x plus 4 is equal to negative 2. At the upper end, we have the x plus 4 is equal to 2. And if I isolate x, so we take 4 away from both sides in both equations. So if x plus 4 is equal to negative 2, and I take away 4, it's going to follow that x is equal to negative 6. And for x plus 4 is equal to 2, taking away 4 again from both sides, and we have that x is equal to negative 2. And just for the x-intercepts, I have 2 of these. Now, without the coordinate display, I have x equal to negative 6 and x equal to negative 2, but displaying as coordinates, again, we have negative 6, 0, as well as negative 2, 0. So I have 2 x-intercepts here. Now for the y-intercept, I'm doing a role reversal. I'm looking at now setting x to 0 and solving for y. So in this case, I'm going to have that y is equal to f of x and setting x to 0. So y is equal to f of 0. And that's equal to 0 plus 4 squared minus 4. So you got y. 0 plus 4 is 4. We'll raise that to the second, take away 4. So we have 16 minus 4. And 16 minus 4 is 12. So I have that y is equal to 12. And just identifying that intercept, again, you can denote in either of 2 ways. So for the y-intercept, you have y is equal to 12. And in terms of ordered pairs, okay, this is going to come out to 0, 12. All right, so just taking what we have all together. Okay. So once again, okay, we had that f of x is going to open up. Yeah, so after determining a, h, and k, graph opens up. Axis of symmetry we have at x is equal to negative 4. And again, the vertex we have located at negative 4, negative 4. For the x-intercepts, okay, so I'm going to have, so I got negative 6, 0, negative 2, 0. For the y-intercept, okay, I have at 0, 12. Okay. Now if I identify at least 5 points, okay, so this is what we have in the makeup thus far. Okay, so I got the graph of f of x equal to the square of x plus 4 minus 4. Okay, and we got key points here. So I got the vertex at negative 4, negative 4. The x-intercepts we have at negative 6, 0 and negative 2, 0. And again, we have the y-intercept at 0, 12. And again, we have the axis of symmetry again, we have x is equal to -4. And it says to identify at least 5 points. Well, guess what? The vertex is 1 point. And I got two x-intercepts, -6, 0, -2, 0. And then I had the y-intercept at 0, 12. So far I have only 4 points identified. And what you can do is that you can use the axis of symmetry to supply a fifth point without having to do any equation modification. And what I mean by this, okay, if you notice, okay, so you have -4, -4, and both the left half and the right half should mirror each other with respect to the axis of symmetry. Okay, so if you were to go up, okay, so you have on the x-axis, you have -2, 0 is 2 spaces to the right, and -6, 0 is 2 spaces to the left. And if I were to go up the axis of symmetry out to y is equal to 12, guess what? The y-intercept is going to be 1, 2, 3, 4 spaces to the right. And mirroring across, if I go 1, 2, 3, 4 spaces to the left, I can supply a fifth point right here. And so for what we have in the case of this particular fifth point, it is level with the y-intercept. Y-intercept again is 4 spaces to the right of the axis of symmetry. This point is going to be 4 spaces to the left of the axis of symmetry and level with the y-intercept. This ordered pair is going to be at x is equal to -8, and since it is level with the y-intercept, you say we have -8, 12. Okay, so you say this is just going to be our, it doesn't necessarily have to be this one, but if you're to quickly use the axis of symmetry, this would be one straightforward choice. Okay, something that lines up and is level with the y-intercept. So we have -8, 12 as a possible fifth point to identify. Okay, now again, there are two forms in terms of displaying a quadratic function, and in terms of how these displays sort of translate in terms of converting from one layout to the other. Okay. So if you're looking at conversions, okay, so if we're looking at converting between standard and vertex forms. Okay, so for converting between standard and vertex forms. Yeah, so you have for the standard, okay, we have y is equal to f of x. Okay, is equal to ax squared plus bx plus c. And again, with the vertex form, again, we have y is equal to f of x. That's equal to a times the square of x minus h followed by k. Okay, the a is the same, okay, but now I'm switching up from expressions with the coefficients b and c to those with the letters h and k. And in terms of how these forms correspond, and let's say if we have an application, and let's say that if we have something that is in standard form to convert, Okay, so if I have converts f of x is equal to x squared plus 6x plus 8 to its vertex form, and then determine the vertex. Okay, so we have, starting out, okay, so we have f of x is equal to x squared plus 6x plus 8. Again, so this is the standard form. And what I'm going to do is that as I proceed going from the standard to the vertex form, I'm going to put parentheses. It's not factoring by grouping, but something akin to factoring by grouping. Okay, it's going to be using parentheses. And what I'm going to do here is I'm going to put parentheses around the terms with the letter x. So we have parentheses around x squared and 6x. So I have f of x is equal to the quantity of x squared plus 6x. Now, what I wanted to do here is I want to form a square trinomial by adding a necessary term or constant to x squared plus 6x. Now, a square trinomial is a trinomial that will factor out to the same binomial times itself. And I'm going to go through a process that's going to be referred to as completing the square. And looking at completing the square, what this is going to mean. Okay, so again, I have the same expression. Okay, so what we're going to have in the process. Now, for what is in the parentheses, you want the leading term inside the parentheses to be just x squared or y squared, whatever variable you're working with. You don't want any numerical value in front. So with x squared as the first term, to complete the square, I'm going to look at the first order term, take its coefficient, and the coefficient of the first order x term is 6. So to complete the square, I'm going to take half of that number and then square out. If the number had been like 1/2, 3/4, 1,000, I'll still be taking half and then squaring. So you got half of 6 is 3. And 3 squared is equal to 9. Now, the follow through is going to be a little bit of a balancing act. And we have f of x, again, so we have is equal to x squared plus 6x, and with the 9, I'm going to add this to x squared plus 6x. Okay, but I want to keep everything in line with x squared plus 6x plus 8. Notice by adding 9, I have at this stage x squared plus 6x plus 17, but I want to get it back level to 8. So I added 9 at the front. So to keep it level, I'm going to subtract 9. So I added 9 at the front. So at the back, I'm going to subtract 9 just to keep everything level. So now I'm going to have f of x is equal to x squared plus 6x plus 9. And 8 minus 9, that is going to become negative 1. And I'm getting closer to the vertex form. Okay, so we have a square trinomial with x squared plus 6x plus 9. Okay, now our k value is going to be at -1. Now, for x squared plus 6x plus 9, we now have a square trinomial. From x squared, I have the square of x. But now for the constant that will be filled in, used to fill in, okay, if we go back, okay, now in terms of how we arrived at this stage to get to this 9, I got it to exist through squaring out +3. So whatever value I square out in the completion of the square process, that is going to re-enter the scene once we get to the vertex form. So I squared out +3, and guess what? I have f of x is equal to the square of x plus 3 minus 1 So we have, in effect, okay, so I have f of x is equal to the square of x plus 3 minus 1. Okay, and so that is going to be the vertex form. Okay, and as for the vertex itself, just looking at what we have from the vertex form. So right away, let's go ahead and write this up. Okay, so if you notice, okay, we have the a is equal to 1. And from x plus 3, if x plus 3 is equal to 0, we have that x is equal to -3. So in effect, okay, we have x is equal to h is equal to -3. And once again, we have with the k value. K value is equal to -1. And so it's going to follow that for what we have in the case of the vertex. Okay, vertex HK, that is going to be situated at -3 and -1.